Thank you, Cameron. It's my great pleasure to come back here 15 times. 15 times, did you say? so I remember, I think it was the last summer here that Cameron and I started discussing the relation between correction to Bekenstein-Hawking entropy and the topological string amplitude, the low energy effective action compute, which topological string compute, and so that led to some interesting work. So since then, we had a lot of wonderful discussion with many participants here, mostly about supersymmetric theories, I guess. And but today, for this summer, we are to focus more on non-supersymmetric cases. And of course, the strength of supersymmetric theory is that you can make lots of constraints. There are lots of constraints about actions that you can write down, and then you can make a stronger statement. But there are other hints. So I think during this workshop, there are various, most of what we can say about quantum field theory can be summarized in the language of low energy effective theory. So there will be various aspects of that discussed today, but in this workshop. But in this talk today, I would like to focus on constraint on low energy theory of consistent quantum theory of gravity. Namely, by assuming that the theory is going to be eventually upgraded into quantum theory of gravity, by making that assumption, what kind of constraint can we get? So then there are actually a few non-trivial things that you can do. And from the point of view of standard low energy theory, suppose you have some UB quantum field theory and then you have some low energy effective theory. Generically, one would think that you can write down any low energy actions that are consistent with symmetry of UB theory. But in the case of quantum gravity, there might be some stronger constraint. And there are a couple of reasons to think about that. One is that in gravity theory, you have some non-trivial UB-IR relations. So for example, if you collide two energetic particles together, if that center of mass energy exceeds Planck mass, then black holes start forming. But then as you increase the energy, the black hole starts growing. So namely that to try to go to UV beyond Planck scale, you start seeing some IR effect. So there are some non-trivial UV-IR mixing when you start introducing gravity. So that give us some hope that there might be some non-trivial IR prediction on observable phenomena that may be deduced from UV completion of quantum gravity. And there are another possible way to think about that is the dangerous irrelevance. That Eva liked to say. Eva actually had a very nice short essay on this recently on arXiv, I think last month. And so the way, so I think Eva can say probably much better than I can, but suppose you have some low energy effective action, which include kinetic term, and then some potential term. So the potential energy can contain mass term, and then some interactions. So suppose it is in 4 dimensions, the higher order term start to get suppressed by some cutoff mass. There can also be some higher derivative interactions like that. So one would think that the higher order term would become negligible because those are suppressed by some large mass that in the UV cutoff scale. But however, for example, if the field sort of makes some excursion beyond the original mass scale, then this becomes important. So that means that even though from the point of view of low energy perspective, these are irrelevant operators, but these may become important in a way that she said upon long time scale, large field range, and large parameter variations, renormalization group flow, etc. So that means that even though these, from the low energy perspective, these may look irrelevant, but there are certain questions that you may ask for which these play roles. And then you can start getting glimpse of UV physics. So that may be one of the ways that you can start sort of getting constraint on low energy theory or low energy phenomena, even without supersymmetric constraint. And so today I would like to discuss a set of sort of constraints that one may possibly derive from this kind of point of view. So Qumran named this type of approach called as Swampland. Question? That is to say that suppose somebody give you a low energy effective theory and it contains gravity. Today I will mostly consider the case when the gravity has nice geometric description describable in terms of Einstein gravity. So suppose somebody give you that, and then the question is that how can I judge whether it is realized as low energy approximation to consistent quantum theory of gravity with, of course, a nice UV completion, such as string theory. So what are the criteria? So in the first hour, I would like to discuss mostly about constraint on symmetry that can be realized in low energy gravitational theory. And then also, if I have time, discuss weak gravity conjecture and its variations. So those are sort of proposed as condition for low energy effective theories. And then possibly, if I have time, I'll discuss the various consequences of these constraints. So let me start with the constraints on symmetries. Okay, so there have been several laws about possible constraint on low energy theory. For example, about global symmetry. So for global symmetry, the constraint is that there is none. That is to say that there is no global symmetry in low energy effective theory of quantum theory of gravity.
Or even discrete.
I will discuss that. Thank you for asking that. So standard derivation or argument for this conjecture applies, as Jack said, continuous case, and I will review that. However, so I would like to make an improvement upon that, and then try to come up with an argument that apply both continuous symmetry and discrete symmetry.
So you don't count the AF-CFT situation where it can be a global symmetry from the CFT?
So I will mostly talk about, so I would only consider the case when we know exactly what the UV completion is, which is a case of ADS-CFT correspondence. So I will discuss all these from the point of, in the setup of ADS-CFT correspondence.
I just meant the trivial thing that the field theory can have global symmetries because the bulk gauge theory is
So CFT can have global symmetry. Yeah, so I will discuss that. So second set constraints that you can have. So in your case, so question is about low energy effective action, low energy effective theory of gravitational theory. So in the case of ADS-CFT, I'm talking about low energy effective action in gravitational theory in ADS. So I'm asking whether that can have global symmetry or not. You mean space-time symmetry. So ADS isometry is actually sort of a remnant of gauge symmetry that is not normalizable. So I'm not going to talk about space-time symmetry, by the way. I will talk only about internal symmetry. So the other is the completeness hypothesis. So this is called, there is a hypothesis about quantum theory, which is often called completeness hypothesis. This is a claim that if a low energy effective theory of quantum gravity contains a compact gauge group G, as I said, there are no global symmetry, so it has to be gauge symmetry, then there must be physical state in every finite dimensional unitary irreducible representation of that group. So for example, the claim is that suppose you have a gauge group U1, compact U1. So then you can have Dirac monopoles. So then this completeness hypothesis says that you should have complete spectrum of electric and magnetic charge that are consistent with Dirac quantization condition. So that those are expectations. Now, so clearly this is not true in every low energy effective theory. So you can certainly easily write down low energy action which violate either of these. For example, you can have pure Maxwell theory, your Maxwell theory without any charged matters, for example. That would violate the second condition. Okay. Now, so quantum consistency, ultraviolet, I'm going to say that ultraviolet completion with gravity requires these constraints on low energy actions. Okay. So let me first review. So the reason that.
Is that a statement about the very low energy theory? I mean, the very low energy, below the electron mass.
Thank you. So for example, charged matter may be black hole. Charged object may be black hole.
No, so those aren't objects.
These are physical. Yeah.
No, yeah, I'm not sure what IR means. I mean, those.
Yeah. So there are all these questions, and the purpose of this talk is to give you as much as possible precise statement towards the end of this talk, so that we can clarify all these questions. So maybe we can discuss that as we go on, and then try to see in what way that I'm referring to as physical state in this context, for example. May I continue that way? So let me first review a standard argument. So the standard argument is the following. So suppose group G is no-abelian Lie group. So here comes the question. So Jack asked whether we are considering continuous group or not. So this standard argument applies to continuous group. So suppose the group. So suppose you have a. So I'm trying to sort of argue for one by contradiction. So suppose you have a global symmetry group G, which is continuous and compact, such as some Lie group SU2 or something. So these Lie group typically have these group have arbitrarily large irreducible representations. The irreducible representation of arbitrarily large dimensions. For example, SU2 can have any high spins. Okay. So then what you can do is that start with some charged matter and then combine them together to make black hole. But then black hole can have arbitrarily large representations. And then let it decay. So it decays. And then, but keep the representation very large. But then the mass of the black hole can become small, but try to keep this bigger than Planck mass so that Bekenstein-Hawking formula still applies. Then you can easily set up a situation where the dimension of representations bigger than the number of states that black hole can have by Bekenstein-Hawking bound. So that's a contradiction. So namely, unless a black hole lose charges, but that is very hard to imagine because Hawking radiation is purely thermal. So if the theory is G invariant, then thermal radiation should be G neutral. So then the charge will not escape, but if the symmetry is preserved during the process, then you get into a situation where you have a bigger representation than the Bekenstein-Hawking bound allows. So that seems to be contradiction. Okay. Of course, you can worry about whether such argument is a good one or not. So, for example, how do we know that Hawking radiation is totally G neutral? Well, it's a sort of statistical thing. So maybe there can be slow leakage of G charges, and then everything is fine. But more seriously, for example, as Jack asked, how about discrete group? So, for example, yes, you have a.
What if you have all representation?
Sorry?
Just take a case when you have not just all representations of things.
So all representation. Yes.
Some of all representation.
Yes.
Then the argument.
Why is that? Could you explain?
Because there is no large representation.
No, I'm saying that suppose you have a mass of black hole, then there is an upper bound on the number of states you can accommodate in that black hole. Suppose I set it up so that that black hole has a big dimensional representation. That's already a contradiction, isn't it?
You need actually smaller.
I need smaller one. The big representation won't fit into black hole. But by combining that with Hawking radiation, I can easily engineer a situation within low energy effective theory where you have a big representation black hole with small mass. So that's contradiction. So that's a standard argument, the way that I understand it. So there are various variations of this argument, but this seems to be a cleanest way to state the standard argument. I'm not going to defend this argument because I hope we will give you better argument, but here is an argument. So and then I'm going to criticize that. So one criticism is that Jack says that this doesn't explain discrete symmetry case. So for example, sorry? Yeah. Yes. So Z2, for example, is also an example where you have either trivial representation or one-dimensional representation where non-trivial element is represented by -1. So then this argument doesn't work, right? So that's a problem. So and then there are also you want to also extend the argument to allow. So these days there are interesting higher form symmetries, P form symmetries. So what are these guys? So you would like to have more uniform argument that sort of covers. So so I'm going to say actually that this applies to discrete symmetry. So it's better. We better have some kind of argument that captures all these symmetries. So. And then there are also empirical evidences for all of this, which is that this is true for all non-string compactification. But of course, that doesn't explain why this has to be true. Okay? So what I would like to talk in the next half an hour or so is to prove refinement of these. So these are not stated precisely enough. So I'd like to make a refinement, and then in the context, refinement of this conjecture in the context of ADS-CFT. And there was actually a nice early work. So let me write by work by Daniel Harrow, 1510-07911. So it's almost a couple of years ago, where he discussed this issue in the U1 case, and then what I'd like to do, and this is in collaboration with Daniel Harrow, is to generalize and extend this early work to cover as much as possible and as precise as possible all cases. So what I would like to claim is that like the first statement here, that any global symmetry and then discrete or continuous is inconsistent with local structure of dual conformal field series. And I would like to tell you what I mean by local structure. And conversely, if the holographic conformal field theory has a compact and again discrete or continuous global symmetry, then the ADS theory has to have a gauge symmetry in the same group.
So this only covers the case where they're holographic dual.
So the converses.
Yes.
So converses, yes. And because in the converse case, which is that when you have symmetry in conformal field theory, if the dual is strongly coupled to gravity, then I don't know how to make a statement. So for example, the problem is that the gauge symmetry is a redundancy of description. So for example, so therefore, it does in general, in a general setup, it doesn't make sense to ask what is the gauge symmetry of the theory. And in fact, we have many examples where you have dual description of given gauge theory. So for example, you can have low energy effective theory with two different gauge groups, for example, are dual to each other in UV, for example. So the statement even does not make sense. However, if you sort of require that a holographic dual to have weakly coupled description, and then it makes sense to ask what is the gauge symmetry it is. So I will make more precise statement later. But that is another reason.
You're not making a general statement. You're making only things which have holography in part of the description.
All my statement is about low energy effective theory in ADS. So what first statement is that those don't have a global symmetry. And the second statement is that if there is a dual CFT, then the symmetry of the dual symmetry can be visible as gauge symmetry. Okay, so that's a statement. And then the third statement is this compactness hypothesis that there must be physical state in every finite dimensional irreducible unitary representation. And then we have some argument with some additional technical assumption about conformal field theory, which holds in all examples we know of, that in fact this symmetry has to be compact, which means that in continuous case it's a compact symmetry, and this discrete case is a finite group, or embeddable in a compact continuous group. Okay, so that's sort of what I would like to do today. And let me move to the other side. So first of all, I need to define what we mean by what are the class of symmetry that we are talking about. So global symmetry. In CFT. Okay, so in undergrad, we learned that when you have a quantum theory has a symmetry, then what we mean by that is that you have a group G, and then for every G, you have some unitary operator. Such that the product goes like this, and then commute with Hamiltonian. Okay, so we learned that this is what we mean by symmetry, and certainly that's valid definition. But this is not strong enough for our purpose. For example, you can have a Hamiltonian energy spectrum and pay attention to 42nd energy eigenstate, and just rotate that 42nd energy eigenstate. So that would satisfy these conditions, right? So, but this is not the kind of thing that we can say anything about. So what we want to so I would like to add additional requirement to the class of symmetry so that we can prove theorems. And additional property is that we incorporate locality in CFT. That is that we are only interested in the class of symmetry which acts locally in conformal field theory. So the first statement is that, the first statement is the definition. So you have a Cauchy surface sigma, Cauchy surface of CFT, and then you have a unitary transformation acting on the Hilbert space. But then the second statement is that suppose you have local operator. So X is in the Cauchy surface. Then I require that this U dagger OX U is also local at the same point. So it maps local operator into local operator, and it preserves the energy momentum tensor, etc. So this U is this U. And the third requirement is that this U of G sigma is faithful in G. That is that, so you should be able to find operators that faithfully make representation of the group G. This condition is important when you want to identify symmetry in the bulk and boundaries. For example, if you have, whether you have SO3 or SU2, this requires different sets of operators, for example. So these are sort of minimum requirements that we'd like to make for, how many blackboard do you have? Okay, so you have, look, yeah, so and then this goes up to, yes, thank you. Yeah, so actually, this can be generalized to the case with anomaly. Yes, and then so for simplicity today, I will only discuss symmetry without anomaly. But we actually most of what I'm going to say apply to symmetry with two-fifth anomaly. That is that the symmetry that is preserved in trivial background, but can be triggered by turning on a gauge field coupled to it, or in some non-trivial background geometry, in the case of mixed gravitational anomaly. Yes, thank you. Yes, that's, yes, thank you. But today I will not talk about the case with anomaly. But some of what I'm going to say applied to those cases as well.
Of course, most of the bulk is not described by local operators. It's
Sorry?
dual theory.
Right. So this is about boundary CFT.
Yeah.
This is about boundary CFT, and then we'll discuss what happens if we look at this in a bulk point of view. Now, so if you have this kind of symmetry, and if this theory has Lagrangian description, and if the symmetry we are considering is continuous, then we almost sort of can prove this, what we want to prove. Because if this is a continuous symmetry and if there is a Lagrangian description, then there is a Noether current. And if you have a Noether current, then this symmetry generator is roughly like, well, in the case of U1, it's exponential of integral of J0. And if you have a Noether current, then by ADS-CFT dictionary, you have a dual gauge field in the bulk. So the symmetry is gauged already. So you already see that you're already getting a glimpse at how requiring sort of global symmetry in conformal field theory implies the gauge symmetry in the bulk in the case of continuous symmetry, right? This is not a very rigorous argument, but this is an argument that we can try to push in the case of continuous case. The problem with this is that, we don't have such Noether current in the case of discrete symmetry, so this argument does not extend to discrete symmetry case.
One more question.
Yes?
Can you assume that the rule for global symmetry rule is actually fine? Can be like
Let me see.
Hirosawa is not a symmetry. There's no symmetry. It's a spectrum generator. It's not a symmetry. Spectrum generating is not a symmetry.
Well, there might. So you're asking whether there is an infinite. So I think that I'm going to make statement about the class of symmetry that with properties that I'm going to describe, and there might be infinite dimensional group that satisfy this group property.
It's not local. I know, but he was assuming locality.
That's also not a finite dimensional subgroup.
Sorry?
You can apply the argument to a finite dimensional subgroup of that infinite.
Yeah, but that finite subspace can be gauged. Yes, but the rest I do not know.
I'm still confused by something basic. You're applying locality in the CFT.
Yes.
I thought you were asking about the low energy theory in bulk, so you might have wanted to apply that condition in bulk, which would correspond to an action on very non-local operators on the dual CFT.
Well, so you. Okay, yeah. So here I'm defining what we mean by global symmetries that act locally in field theory, and so when we say so actually I'm going to apply it. Okay, so maybe I should have clarified this. Maybe this was not. So sorry.
Subquotient surfaces.
Yes, so I'm coming to that. So actually, I'm sorry. So maybe. So can I?
In the bulk.
Yes. Yeah. So I'm actually I was going to apologize to you, which is that actually so what I wanted to do actually here was to define global symmetry, whether it is in bulk or boundary. And so what actually I'm going to do after defining what we mean by global symmetry, actually I went a little bit I lost the order of my presentation, which is why the confusion. So I'm going to define what we mean by global symmetry, whether it is bulk or boundary. And then first I'm going to apply this definition to the bulk ADS, and then find the contradiction. Does it satisfy you?
Yes, but just so I understand, that means you won't impose this locality condition in the dual CFT because
I will apply, yeah, we'll see how it goes. So what I'm going to argue is that I would like, what I would like to do is assume global symmetry in ADS gravity and find contradiction. So I'm going to, what I'm doing here is spell out what we mean by global symmetry, apply that to ADS gravity, and then find the contradiction. And during the process, I will argue that the global symmetry in ADS also implies global symmetry in CFT with the same property.
You're assuming the notion of local operator exists.
Yes. So I'm assuming that there is a hierarchy of scale in the ADS side, which I have not told you precisely what it is about. But the very fact that I'm assuming that weakly coupled gravity description is valid means that the locality in the bulk is valid up to Planck length. So this is approximate locality, of course, that we'll be talking about. Of course, below the Planck length, the locality does not hold, and you have to do gravitation dressing and all these kind of things that we have to worry about. Okay. So anyway, so this existence of net current we cannot assume, but we'd like to sort of use some feature of that, and then which can be generalizable to the case of global symmetry. And one aspect of having net current and this type of property is that if you have, for example, so suppose this is sigma, and if you divide sigma into subspaces, say R1, R2, R3, R4, etc. So then, then this can be expressed as product of operator acting on each individual sub-Cauchy surfaces. So suppose you divide the sigma into subspaces like that. So since this is given as an integral, then this can be expressed as a product of these unitary operator acting on each individual spaces. So this is a feature that actually generalizes to discrete symmetry cases. Also, if a certain condition on the locality is assumed. So let me give you two more conditions based on that. So one condition is that suppose you have some arbitrary subspace of this Cauchy surface, then I require that you still have this unitary operator such that this unitary operator generate the transformation if X is in R, and then does not act on it if X is not in R. So namely, I require that there is such an operator. And then additional one more condition is exactly this. With this definition of local unitary operator, then if you consider sort of if you divide the space into unions, then the local operator becomes product. As I said, if you assume a Lagrangian description of quantum field theory, and if the symmetry is continuous, then 1, 2, 3 implies 4, 5 by the Noether theorem.
And assume no anomaly.
Yeah. As I said, I'm assuming that there is no anomaly during this talk. More generally, it has been shown by Buchholz, Duplicher, and Lungo that if you assume a certain splittability condition for quantum field theory Hilbert space, then then this holds for any symmetry group. That is to say that if you have a quantum, so we can discuss how valid this assumption is. But suppose you have a quantum field theory defined in some space like Cauchy surface sigma, and then divide that into segment. Then you can define Hilbert space to be essentially the tensor product of Hilbert space associated to each subspaces. Now, there are an issue about how to do that, for example, in the case of gauge theory, for example, because there are variables associated to links rather than sites. So if the quantum field theory have a UV description in terms of lattice model where degrees of freedoms are all located at the lattice, then you can do this at the UV level and then define it like that. In the case of gauge symmetry, where there are variables on the links, there are some subtlety. So when you divide the Hilbert space into this, then you may have to define boundary condition. Typically, what you can deal with that is that you can try to set up so that gauge symmetry is emergent, so that in fact in the UV you have sort of local degrees of freedom, and then you can make splitting at that level. Of course, then this division will be UV sensitive, but that UV sensitivity is actually only about the boundary between the regions. And for the purpose of my argument, in which follows, it is sufficient. What it means is that in a situation like that, instead of this, this can have this product structure times some additional operator that is acting only on the boundary between the regions. And but that is actually good enough for the purpose of my argument below. So that is sort of what I'm going to assume. And then if you assume this kind of splittability, then this essentially follows. So let me give you a brief argument for this. Yes? Somebody had? Yes, please.
Really simple. I mean, here, these U's are in some group.
Yes.
And here we have a product over I.
Yes.
And is there any ordering issue associated with it?
So each one of them is assumed to be acting on separate Hilbert spaces.
Yes, I see.
So they're all supposed to commute with each other.
Yes. And they're acting on different things.
Because it's this Cauchy.
Yeah, so I'm assuming that the sigma is, I should have clarified this. So I'm assuming that sigma is divided into these. And then so what I'm asking is that, well, you have local symmetry in the quantum field theory. So if this symmetry is acting locally, then you should be able to define operator individually in each region. And then whole symmetry generated is just a product. So that's the kind of statement. You look very uncomfortable. So.
Technical comment should be that the formula should not apply what X is in the boundary of R.
Right. Yes. So all these. So this equality here is modulo operator on the boundary, and here is too. So you're asking about what happens. Okay. So I think I should have put bars here, for example, and R is open. Would that satisfy you?
Yeah.
Thank you.
Can you say again what you were saying about the gravitational dressing?
Yes. So here I'm only requiring, so in the bulk, when you have cutoff at the Planck scale, then probably to become clear after I give the argument. But then you will see that it's sufficient that this kind of locality is valid up to Planck length. So we can make the set up the argument in such a way that if the locality is valid only valid up to sufficiently small length scale, then the argument goes through. May I continue? Yeah. So okay. So maybe because what time we started like 15 after. So may I take another 20 or something before the break? Yes. So maybe so I can try to explain how this follows from this, but maybe rather than going into that, maybe I should just give it an argument, because the argument is once I have set this up, the argument is fairly straightforward. And then, but this is sort of important technical assumption, and if there are discussions, so I'll be very happy to engage in discussion on the validity of this type of assumption, etc., which is actually very important. But given the time constraint, let me first go straight into the explanation of why this leads to this type of derivation. So the main idea that we are going to employ is entanglement wedge reconstruction. So there has been very important development in ADS-CFT correspondence about how we can probe locality in ADS from the conformal field theory perspective. And it was discovered that the way that ADS-CFT does has close connection to the class of states that used in quantum error corrections. And this has given us very interesting insight about how sort of ADS-CFT works microscopically. So the insight was the following. So suppose you have, for simplicity, let's consider the bulk to be pure ADS. It can be applied to other background, but suppose you have a pure ADS background. So this is, so you have an ADS. So suppose this is a space like Cauchy section of ADS, so which is a hyperbolic space. And then you have a boundary CFT. So suppose you have some Cauchy surface, subspace of a boundary. So this circle represents the entire Cauchy surface of CFT. And then entanglement wedge reconstruction is an idea that not only the entire Cauchy surface of CFT carries the information about entire bulk gravity, but if you restrict yourself to weakly coupled gravitational situation, then there is actually a well-defined subspace, subregion in the bulk, which corresponds to subregion in CFT. And in the simplest case of pure ADS, it is delineated by the Ryu-Takayanagi surface. So this is the Ryu-Takayanagi surface in the bulk. So the claim is that any local operator in this region can be reconstructed as operator acting on this region. And then the complement is not. So that is sort of subregion duality statement. So if you have, but this is only for some particular subspace of bulk gravitational system and subspace of conformal field theory, where you have well-defined geometric bulk gravity, and then there is some local excitation here. That state have corresponding state over here. So that is sort of idea of entanglement wedge reconstruction. This shaded area is called entanglement wedge. Actually, it's a space, so some Cauchy development was that included. Now, so this led to some kind of curious puzzle that was clarified in the last couple of years. And that is the following. So suppose you have, suppose you divide the boundary into 3 segments, say A, B, C, and then A, B, C. And then suppose you are interested in understanding, sort of describing local excitation in the middle of ADS. Well, suppose if you look at the entanglement edge for A, it won't cover this region. So that means that local excitation over here cannot be describable in terms of operator acting on A. And the same is true for B. Same is true for C. So that means that this local excitation cannot be described by any operator on this side, and this side. That seems already a bit funny. But even funnier is the fact that even though this cannot be described only in terms of A or B, but if you combine A and B, then the entanglement wedge would cover this local region over here. So that means that there is some information that you can extract if you combine these 2 spaces here, which cannot be obtainable by individually considering region A or region B separately. So this leads various people to realize that this local information about this local operator is encoded in the boundary CFT in a particular entanglement information. That is that the information here is encoded in the entanglement between A and B, and not by A or not by B separately. And then it was realized that the way this is done is very similar to how people had used already in the context of quantum information about encoding information in a way that you can correct later. So this leads to various realization that ADS-CFT actually, in the context of ADS-CFT, the holographic state in CFT, which is to say state which has weakly coupled gravity description, has particular entanglement structure. So in passing, I would like to advertise that I have also had some work with Nim Bao and the collaborators, where we try to sort of capture some of these entanglement information in terms of inequality between entanglement entropy in holographic state, and we are able to classify them and derive some certain property of this inequality. So I close the parenthesis. And then, but now, so I'm going to use this entanglement wedge reconstruction to lead to derive the claim. And again, so I'm going to use I'm going to the proof of one, which I already raised, which is to say that there are no global symmetry in quantum gravity in ADS. And so by contradiction, that means that suppose ADS gravity has global symmetry G. So I start with that. So that means that the symmetry, bulk gravity theory has this kind of property. Okay. So in particular, so that means that there must be some local operator. There must be local operator O of X in the bulk, which transforms faithfully under this group representation G. Okay. So that's an assumption 2 and 3 over there. So, but this operator can be brought to the boundary here. And then since there is a global symmetry operator acting on ADS, so that means that CFT must have the same symmetry. So that comes with all the bells and whistles of associated to this symmetry. So in particular, that means that symmetry generator can be expressible as product. Yes?
The symmetry may be local in ADS. Why does it have to be local in the CFT?
Well, so you can bring this to the boundary, and then you can also, if you have this, then you can divide it.
It's not about the O's, it's a statement about the U's.
Yes. The global symmetry in conformal field theory satisfies these properties.
I know that, but the statement that the symmetry was local in the bulk is a statement about the U's, not about the...
Yeah, so it's a question about, so now it's a question about how much we can sort of argue for this property for general quantum field theory. I was trying to argue that for any quantum field theory, local symmetry satisfying 1, 2, 3 satisfies these properties, including conformal field theory.
I understand, but the statement that there's a...
So 1, 2, 3 is true.
But I don't even see 1, 2, 3. 1, 2, 3 is true of the bulk theory. I don't see why...
Because I can bring this operator to boundary. So the bulk state there is a correspondence between bulk state and boundary state. So I can bring this state to the boundary and construct an operator which is in the faithful representation on the boundary CFT.
The assumption is that everything from the boundary can be obtained from something above.
Right.
That everything...
Yeah, but in particular, so there are such operator. There must be such operator in CFT that also faithfully represent the symmetry. Yeah. Because I can bring the operator to the boundary.
Yeah, that's we say as an extra conditional.
Yeah, it's an extra. It seems to me like an extra condition.
That's part of the duality.
Yeah. There is a set of ADS-CFT dictionaries that I assume in this presentation. Okay.
Okay.
So in particular, this property, however, can also be, derivable because you can, if you have a division of the bulk, I can divide the make a corresponding boundary. But if you get a symmetry that satisfies this condition, then the symmetry generator. So if you have so now we have a boundary, and you can divide the boundary into segments. Boundary Cauchy surface into segments, R1, R2, R3, R4, etc. So the symmetry generator can now be divided into symmetry generator acting on this segment, this segment, this segment, this segment. Now I ask, well, so you have this operator acting on each of these domains. So for example, acting on this operator can reconstruct this region in the bulk. Operator here can reconstruct this region in the bulk. So the point of this construction, and this is related to the question of George, that is that I'm constructing this unitary operator as a product of operator acting on each individual region, acting as a product. This operator does not generate any entanglement between different regions. So that means that this construction shows that this operator can only act on the shaded region in the bulk. So in particular, commute with this operator located at X. So this is a contradiction. Namely that if you assume this type of decomposition to hold in the boundary, then you cannot construct operator. So you cannot have local operator in the bulk, which has non-trivial commutation relation with a boundary unitary operator realizing this symmetry. So this is. Yeah. Thank you very much. So yes. So now I'm going to clarify various issues. Let me start with the question of Eva. So Eva asked, well, so in the bulk theory is gravitational. So that means that Kumura also asked. So there is no sort of notion of exact locality. So there might be some kind of fuzziness associated to Planck length that you have to do gravitational dressing and etc.
Well, not just bulk, like stringy.
Yeah. So, but we can divide the boundary as small as you like. So you can, if this reaches. If you are worried about sort of overlap of this wave function with these regions, I can divide this into half and significantly reduce the overlap. I can reduce it as small as possible.
The worry is that the idea of this subregion duality is only valid in the planar limit.
Right. So in the bulk, that would correspond to quantum corrections.
Yeah.
So I'm assuming that in the bulk, I have a weakly coupled gravity description where the leading effect is a semi-classical approximation, and then you can worry about corrections.
You're using the Schur lemma, right? Something like the Schur lemma.
Yes.
But the Schur lemma is only correct rigorously zero, right? If the commutator is rigorously.
So you're worried that even if it is, so 1 over n non-commutativity might cause a problem for us.
That's my question. I'm not worried. I'm just asking how do you address that?
Yes. Well, so this depends on how you use Schur's lemma. So here, here the requirement is that this should commute with order 1.
Yes.
This should anti-commute with this with order 1, not just 1 over n, essentially. Right? Yes. So I'm happy to stop here and then I'll take more questions because this is short proof. So yes.
You say it doesn't matter that O of X where you drew it is actually reconstructed by some very non-local operator on the field theory side.
Well, the claim is that the operator here. So the assumption is that if the operator is not in the entanglement wedge, then you cannot reconstruct. It's assuming that I'm assuming that it's local in the bulk. I don't care how it is realized on the boundary. So, for example, typically entanglement wedge reconstruction actually implies that the local operator is reconstructed non-locally, because, for example, this shows that this cannot be reconstructed locally in A and B, because if it did, then you should be able to tell the difference between the two, right? So I think that entanglement wedge reconstruction already sort of assumes, I expect, I should say, that the local operator in the bulk is constructed non-locally in the boundary.
Right. So can't the U of G act on act on it the right way to construct the representation?
Well, so the problem of U of G is that it's a product. It doesn't generate any entanglement. So what the lesson we learned from entanglement wedge reconstruction is that in order to construct operators that have non-trivial action in the middle, so that it has order 1 non-commutativity with this local operator, then you have to generate entanglement.
But then U of G can't have a piece that just acts non-locally on the operator.
Sorry, so U of G.
Acts on the non-local operator that produces O of X.
What is a non-local in the boundary or bulk?
In the boundary.
On the boundary, yes.
In the dual CFT.
So U of X indeed is expected to be realized non-locally on the boundary. So I don't see any contradiction with that.
So you're saying that the symmetry generators cannot act on that in the right way?
The problem with symmetry generator is it's purely local, like here. So in the case of continuous group, it is just integral of nature charge, right?
I'm confused on why it has to be. Why does it have to be purely local on the CFT side? Could it have a piece that?
So you're asking whether symmetry symmetry G, which is global symmetry in the bulk, can be something non-local in CFT?
That's my question.
Yeah, but the thing is that you have local operator. This symmetry acts locally on the boundary.
It has to act locally on those local operators.
Well,
But could it act?
Well, I think partly again it's related to the other question. His assumption is that the locality of the bulk and the boundary are related in the sufficient neighborhood
No, I
of
think
the boundary, in which case they can translate the locality of the
You may
operators
think that there
and
could be,
symmetries.
but you may think there could be something that acts locally on local operators, but is inherently non-local.
Right. It acts correctly on the local operators, but it also has some piece that acts on O of X.
That would be beyond what we normally think of as symmetry as CFT, but
Right.
I mean, it could be
Right.
like the first example that you gave. You just take some random eigenvalue. And
Right.
project it.
Right. Exactly. It's the question.
So you're asking the following situation. So you have, of course, CFT Hilbert space is much bigger than the semi-classical Hilbert space of bulk gravitational theory. So in here I have only access to semi-classical. So from the bulk point of view,
To me, it's not a question about going beyond the semi-classical. It's about whether there could be a symmetry in the CFT whose generators aren't these purely local things.
yeah, but
Which do act on the local.
But if I can stay in semi-classical, if you, okay, so may I just try to complete what I was trying to say? So what I want to try to say was that CFT Hilbert space is bigger than of course, the weakly coupled gravitational Hilbert space, and so in the weakly coupled gravitational Hilbert space, I'm assuming the symmetry being local in the bulk. So in that sector, that symmetry is also that is also realized locally in that corresponding subsector in CFT, right? Because so there is a well-defined subspace of CFT Hilbert space, which corresponds to bulk gravitational.
So that's the step I'm missing. And
Okay.
I
Yeah, please.
should not put it on any.
Yeah, because beyond that, I don't have a statement.
I
Yes.
understand that bulk O of X can be moved to the boundary, but as you move it, it's described very differently in the CFT. It's not as though it's the same thing as you move it toward the boundary.
Yeah. But so yes, I agree with that. But nevertheless, it is true that if I can move this operator to the boundary, I can construct a local operator in the boundary which acts only on that point in the boundary.
So there is such an operator, but could the generators of the symmetry you're talking about be dressed up with in some way that acts on direct, on the O of X when it's realized where you put it as something that would be described by a non-local operator on the field side? I may just be confused, but this is my question.
Okay, so let me try to address that. So do you agree that first of all, I can restrict my attention to subspace of conformal field theory Hilbert space, which correspond to weakly quantized back gravity, because that would make things well defined. So let's say that. So then I know entire sets of charged state in the bulk. There is no sort of mysterious state coming in because I have a Lagrangian, I have a low energy effective action. May I?
The restriction to that subspace isn't local on the boundary. That's the confusion that all of us seem to have. There is a subspace of the boundary theory that corresponds to low energy bulk modes, but that's not local.
No. Can I?
May I make a suggestion? Given that maybe there could be a discussion. It's a good point to make break
Sure.
discussion for 15 minutes, and then we'll come back and then
Okay.
the half hour.
Yes.
Start around 11:30.
Okay, I'm happy with that. Thank you. Finish reasonably. So.
You're the only one standing.
So I try to argue that if you make this assumption about how symmetry generates act on the boundary, then the local operator sitting in the middle would commute with this. So that means that this cannot act non-trivially on this. And then, so that was basically the argument. And then, so I think this is a strong assumption. We should discuss in more detail, and I'll be happy to discuss that. But it's probably worthwhile to mention that why gauge symmetry avoids that problem. So what this means is that if you have symmetry, conversely, if you have symmetry in the boundary CFT, then it cannot be global symmetry in the bulk if it has to be gauge symmetry. But in that case, there is no contradiction, because if this is a gauge symmetry, then the charged operator cannot by itself sit in the middle bare, because it has to be attached with a Wilson line operator to make it in gauge invariant.
How about the loop?
Yes? Oh, yeah, so there you can talk about various other extended operators, and I can go into.
Tiny circle.
Well, but what do you mean by loop? But the loop doesn't have end point.
Yeah.
But then this is charge neutral. Loop is gauge invariant. But I just wanted to see how we can see charge the local operator. But charge the local operator in the bulk has to come with Wilson line. But then Wilson line has to end somewhere on the boundary, and then you can detect it with this operator. So that means that this operator does not commute with this one. And that's okay. That's what we expect.
Sorry, can't you have just 2 points in the middle with a line?
But that would be neutral again. So if you have 2 points in the middle, so then this and this should be sort of a conjugate representation. So then this would commute with this, and there is nothing wrong with this. This is gauge invariant. So this would commute with this operator. So gauge invariant operator commute with this is charge neutral. So non-trivial operator is this kind of things. That has a non-trivial. So if you have gauge symmetry in the bulk, boundary CFT has global symmetry. By definition, it has to have charged operator. This is a charged state. And then you can ask, can you construct any charged state, etc.? And yes, indeed, because suppose instead of pure ADS, consider ADS Schwarzschild geometry, like that. So then, as Juan Marcena pointed out 15 years ago or so, that this state corresponds to particular entanglement state of 2 copies of conformal field theory Hilbert space, the sum field double state. And so then consider, so here I consider Wilson line operator here. We can also consider Wilson line operator connecting these two. Wilson line operator can be constructed for any faithful representation of the gauge group G. So that means that you have to have an operator which acts as a representation R in the faithful representation R for the gauge group G and the dual of that acting on this. So that means that these Hilbert spaces have to allow such charged excitation because it's a tensor product. So this already shows that every irreducible representation, faithful irreducible representation of the group should appear. Okay, so this is almost a proof. I can, in view of time, let me move on to another topic that I wanted to cover, which is, I'm afraid, maybe even more controversial, which is the weak gravity conjecture. Okay, so there are various variants of weak gravity conjecture with various degrees of certainty. So let me try to discuss that. So that it is a statement that if you have a low energy effective theory with Einstein gravity plus Maxwell plus charged matter, then there must be, among this charged matter field, there must be a particle. Charged matter should include a particle of mass m and q such that m is much less than Planck and m is below, m is smaller than charge measured in the Newton constant. The precise, depending on the space-time dimension, there are some numerical constants that goes into here, and the precise numerical factor is given by the extremal Reinstein-Orstrom black hole condition. So there is a well-defined numerical coefficient here, which I'm not including here. So there are a few things that need to be clarified. One is that should equality be included? That's one question. And the other thing that need to be clarified is that Q does not have to be fundamental. There can be a situation where, so you have to have such particle. This is, by the way, called weak gravity conjecture, because if you have two of such particle satisfying this, then the Newton gravitational attraction between them would be weaker than the Coulomb repulsion between such particles. So that means that there must be at least one particle where gravitational force acts weaker than the Maxwell force. Okay. So there has been some question about whether this has to be satisfied by, say, in the case of Maxwell U1 theory, smallest charged particle. And the answer is that it doesn't have to be. Okay. So there is also a question about multiple U1. So what is the natural generalization of this condition where there are several U1s? And Cliff Chun and Grant Lehman, who is a grad student at Caltech, who is just graduating, who graduated now, has a nice condition that is the following. So suppose you have several U1 and you write the charge as vector, normalize it with the mass of that particle, then they consider the following thing. So suppose I consider Cartesian coordinate with this charge vector. So I'm just drawing 2 dimension because I'm given 2-dimensional blackboard to work with. Simon Center could have funded 3 higher dimensional blackboard, but so then you draw a circle. You draw a ball, a unit ball. And then you ask, well, you have to have a set of charged particles now, several sets, so that the Z that you can draw. So you have several. So if I had a colored chalk, which I don't, then I would have drawn this. So you have this particle with this charge vector, Z vector. We have this particle with charge vector, you have this particle with charge vector, etc. Oh, thank you. Yeah, so you have this particle, you have this particle, you have this particle, you have this particle, and then you consider convex hull of this, and that convex hull should contain the original unit ball. So this condition is sort of conjecture. Generalization was conjectured by Chen and Raman based on property of Reissner-Norton black hole. I think that there were two basically arguments for the weak gravity conjecture originally. One was the expectation that the extremal black hole should be able to decay unless it is protected by supersymmetry. And the second expectation is that it is true in all known construction in string theory. The Chung and Raman generalized this first expectation that black hole should be able to, Reissner-Norton black hole should be able to decay for multiple U1 case and obtain this conjecture. So I'll come back to that later. So I actually prepared a few examples to demonstrate this, but in view of time, I cannot go through all of these. But let me just mention one. So briefly, so suppose you have a heterotic string on, because this is instructive, compactified on d-dimensional torus. Then this has U1 to the 16 plus 2d charge coming from this toroidal compactification. And this charge is in the lattice. The charge lattice is in the sort of gamma 16 plus d, comma d, which is even self-dual lattice. So there are two situations. One situation is so when mass square is 1/2 of PR square, regardless of P left, and this is called the Davoka-Harvey states, and these are BPS. And this exactly saturates this weak gravity inequality. There is another sequence of states for which m square is equal to 1/2 of m square is equal to 1/2 of p left square minus 1, regardless of right moving charge. And this corresponds to the left moving excitation to be equal to 0. And this actually strictly satisfies weak gravity. So these are non-BPS states. But these are stable and satisfies this inequality without the equality sign. And in fact, in all known example of this type of construction, in non-BPS case, strict inequality is satisfied. Now, as I said, compared to the Swampland conditions that I discussed in the first half of this seminar, no global symmetry, etc., the argument for this is weak. That's why it's called weak gravity conjecture. But I can try to give a holographic argument, and the following was given by Daniel Hall's original work roughly 2 years ago that I cited. So he argues the following. So I already gave this argument that if you have, so let me draw this picture again. So suppose you have ADS Schwarzschild geometry, then you have a wormhole connecting the two Hilbert space. You have CFT Hilbert space on the left and CFT Hilbert space on the right. And then, there is this argument that you should be able to consider Wilson line connecting, let me draw this with colored chalk, connecting two, and then it can be in any faithful irreducible unitary finite dimensional representation of the group. And that I argue that because of that, one should be able to have a charged excitation on this side and this side. But there should be more than that. That is that this is an operator acting on this tensor product Hilbert space, but this Hilbert space is just a direct product. So that means that any operator acting on this Hilbert space, one should be able to write as sum of product of operators acting on this and acting on this separately. So namely that this Wilson line operator, one should be able to write as a sum of product of operators acting on the left and acting on the right, etc. This is not the right way of writing it, but I hope you understand what I mean. So maybe I should say J, J, and J, or something like that. So you have this kind of double sum product expression. So that means that you have to be able to decompose it into operators like that. So one possibility of doing this is that suppose this is in the representation Q and Q conjugate. Well, so if you have such charged excitation, there must be corresponding charged state in the bulk. So then you can create such charged state and express this as a sort of a product like that. So you can cut this by pair creating state with charge Q bar and Q. So okay, so now I have expressed this in. But then there's a question is that how close these pairs should be. Well, suppose you create a state with distance epsilon. Then we should be able to detect the difference between this operator and this operator, because I can try to probe the distance in the bulk shorter than epsilon. So then you can tell the difference. So what should I do? Well, you have to take this epsilon smaller and smaller, but then at some point you have to stop, and because there is a Planck scale. So this type of based on this this line of argument, this line of logic, Daniel Harlow argued that so in order for all this story to make sense, eventually this gauge symmetry should be emergent in the bulk. Because if the gauge symmetry is emergent, then at some point the Wilson line become product of local operator. So then we can do this. So the claim is that so this is sort of so there is a jump in logic, but the claim is that the bulk gauge field must be emergent. Okay, so this line should be strengthened, but this is an argument that if this is emergent, this is satisfied, and this seems to call for such kind of structure. I'm not going to justify this, but I just wanted to point out that if you yes. Gauge field to be emergent means that there is a scale lambda less than Planck scale. Inquisitor. So there must be a scale less than the Planck scale, so that below this scale you have a gauge field, gauge degrees of freedom. And here, okay, so I should also clarify. Now we get into some discussion of what we mean by gauge symmetry. But let me first state that beyond this, you have some non-gauge degrees of freedom. Below lambda, you emerge gauge degrees of freedom. But now you can ask, well, what do you mean by gauge symmetry? Because it's a redundancy of description. So it's a very sort of important philosophical breakthrough made 15 years ago or so, or more, 20 years ago, I guess. Or more, even more, I'm sorry. Maybe, yes. Anyway, so gauge symmetry is a redundancy of description. So I have to be careful who to attribute this. But so this may not be a well-defined statement, but it is in this context, because I'm only interested in the class of gauge symmetry that are visible on the boundary, because what I'm saying is that we are interested in a gauge symmetry where you have a charged state. We can talk about charged state with weakly coupled Maxwell degrees of freedom. So the gauge symmetry should be in the Coulomb phase, where you have long-range correlation towards the boundary. So in that case, I think it's well defined too.
You're saying that the gauge should be emergent if when you put a boundary, there is a new global symmetry. Like if you put your set boundary conditions and there is global symmetry that acts on the edge modes.
Oh, okay. Maybe we can say that. Okay, I have to totally, I cannot really, in real time, be able to respond. But that might be a way to state it. There has to be something to do with long-range degrees of freedom that extend to the boundary. Okay, so I'm going to say that, well, so this if such under such scenario, then this holds. So this is satisfactory. So I'm going to sort of I want to give you an example where, in fact, if indeed gauge symmetry is emergent, then weak gravity inequality follows. So that's how I want to tie this together. So the example that I want to work on, and then which leads to also a convex Hull condition, is so example of emergent gauge theory in CPM model in D dimension. So it is known that when n is very large, there is a Coulomb phase. So that comes with U1 gauge field plus scalar of charge M and Q. And for simplicity, let me just write down the formula for D greater than 4. But there is an analogous formula for D less than 4. So there is a cutoff scalar associated to CPN. CPN model, of course, in high dimension has to be cut off. So if I use lambda as a cutoff, then you have a charge formula. But then, since you have a large number of particles, it's going to renormalize Newton constant. So the G Newton, effective G Newton is 1 over n times lambda of 2 minus d. So then if you consider that kind of combination, Q over square root of G, that's going to be like lambda. But then the mass of that particle should be less than m, because lambda is my cutoff scale. So in order for the mass scalar particle to emergent, then of course m has to be less than lambda. But this is nothing but the weak gravity inequality. And in this case, again, it is strictly satisfied. So interestingly enough, in this kind of setup, we see that weak gravity inequality naturally appear in this way.
Think of this as a way of just distinguishing particles from black holes.
What do you mean?
Well, black holes don't satisfy this, right?
That was one of the motivations. Original motivation was that you have to distinguish black hole from particles. So that when you have an extreme on one end decay, without particles, but the other one to distinguish. So one violates it, one goes the other.
So this is just one example, but this seems to be a generic phenomenon in emergent gauge theory. So let me just try to, in order to impress upon you that fact, let me actually show that similar model can actually produce a convex Hull conditions as well. So let me,
Sorry, the string or M theory isn't really true that the gauge symmetry is emergent in the sense you're saying. You give the CPN model example, which is very clear.
yes. So it's hard to see in the low energy description because this is a statement that goes beyond the about the physics beyond the low energy cutoff. So M theory description is of course given in terms of low energy massless degrees of freedom. So
I don't know if you take a matrix.
well, if you use matrix theory, of course, all gauge degrees of freedom are emergent, including all bulk degrees of freedom.
I'm thinking of symmetry. So I'm thinking of the world sheet string theory, which is not enough for the symmetry.
Yeah, I take perturbative string theory as sort of in a similar point of view as sort of low energy effective action description, except that it includes some non-extended degree. Sorry?
By the time you get to perturbative string theory, the symmetry is still.
Yes, that's what I would think. Yeah. So it's hard to see. Indeed, I agree with you.
In 2 dimensions, I perfectly understand your example. But in higher dimensions, the mass of the scalars is the free parameter. It can be anything you want.
Yeah, but this statement that gauge symmetry is emergent does not make sense beyond this cutoff. So it's sort of tautologically true.
I don't think I agree with that, because you can take the gauge coupling to be very small and the mass to be very, very large, and then you keep the radius of the CPM case.
Okay.
The radius of the CPM to be smaller than the cutoff, right?
So lambda is the cutoff of CPM.
You want the radius of the CPM to be smaller than the cutoff.
Yes.
But you can arrange it by taking the mass to infinity and the gauge coupling to 0.
Mass, which mass? This.
Yeah, exactly.
But this is a free parameter, right?
Yeah. So this is not a duality. This is just saying that.
But in that case, we don't have this setup. So I'm saying that suppose I want to have a Maxwell theory with U1.
Put it this way: if the scalars are actually light,
Yes.
then these things are not dual beyond 2 dimensions, right? You're not claiming that the CPN single model in 4 dimensions is dual to U1 plus n scalars. It's just not true. It's only true in the deep space. In the deep space.
Right. Yeah.
So it's not true. I'm a little confused about this example, but I think in 2 dimensions it's perfectly okay.
Okay.
Because both theories are unique.
Sure. Of course. Yes. I think it still makes sense, but I need to think about that. So I just wanted to generalize this to n, assuming that this is agreeable. So suppose you have k of them. So suppose you consider tensor product of this CPN model. Then if you follow the same logic, then it would give rise to U1 plus scalar of mi and qi. And then so qi square now is 1 over ni lambda 4 minus d. So this is the case because of course it's a decoupled system. But gravitationally they couple. So gravitationally they couple. So therefore the effective Newton constant will be related to all of these degrees of freedom. So then actually it's sort of a simple exercise of linear algebra to show that so the requirement that all these particles have mass below the cutoff is equivalent to the inequality that I equal 1 to k. Just like this inequality is equivalent to the weak gravity inequality, this inequality is equivalent to the inequality that this is greater than 1 for sum over I is 1 to k, lambda I is equal to 1, and lambda I is greater than 0. So this is exactly the convex hull condition that Chen and Remen reproduced. So look like emergent gauge theory scenario reproduce the kind of property that we expect. Okay, so I agree that this is not a very strong, convincing derivation of weak gravity conjecture, but this is some indication that for some class of setup that these inequalities always seems to happen. And also non-supersymmetric setup, which is sort of a focus of this workshop, strict inequality seems to be satisfied. So this led me and Kamran to conjecture last fall that to ask what happens if strict inequality is required for non-R symmetry. That is that the M should be strictly less than Q in the Planck unit when the symmetry we are considering is not related to BPS condition. So this looks like an innocuous additional condition that we do not allow inequality here. But we realize that this actually leads to rather surprising consequences. If this was true, then if you have non-supersymmetric ADS geometry supported by fluxes, then such geometry are all unstable. And the reason for that is actually, so this is this kind of mechanism was pointed out earlier by Mardosen and collaborators. That basically that you can nucleate. So suppose you have some flux in in ADS. So flux is associated to higher form gauge symmetry. So that means that there must be some brane whose tension and charge satisfy similar inequality according to this condition. So then you can nucleate such brane. And then what happens is that suppose you have ADS geometry. So this is boundary CFT, and you have ADS. And suppose you have some kind of n unit of flux, which support this ADS geometry. Then what happens is that you can nucleate brane whose tension is less than charge with respect to this. So then by nucleating this, you can reduce the flux to n-1. But then this brane can reach boundary in finite time. So the boundary CFT would feel this effect in finite time. And then you can ask, well, what is the sort of probability that this nucleation happens? And you can estimate that this nucleation happens at finite probability per unit volume. So, but ADS has infinite volume. So that means that the probability of that happening is infinite. Namely, that means that it happens instantaneously. Well, you can say that, well, this is ridiculous, that in practice you have some kind of cutoff in ADS. And then that corresponds to UV cutoff in CFT. But what happens is that the volume, the ADS volume near this cutoff is very large of order of cutoff scale. So that means that if you cut off ADS geometry in IR and corresponding to UV cutoff in the bulk, then the probability of this nucleation will be at the cutoff time. So namely that, so that means that from the point of view of CFT would not survive beyond the cutoff time. So, which is equivalent to say that CFT does not exist. So,
there are, I think, very compelling claims in the literature that you can stabilize warp compactification, which have such a situation where there's a road at the end of a finite scale. And the claim is it's metastable and not that short-lived.
Okay.
Do you disagree with that? I mean, I have in mind GKT, KKLT.
Let's see. So KKLT, you start with. So you're talking about KKLT have various stages. You start with ADS flux.
Have a non-supersymmetric gauge. You basically, you can avoid the Landau pole of the gauge theory by cutting things off at a certain scale from the gauge theory point of view, and then not encounter this problem. And people have done that by connecting it to a warp compactification for model building reasons. That's why it's fine.
So how precisely this is avoided?
Well,
So.
I guess I didn't follow the argument.
Okay, let me. So I think you can calculate brane nucleation process. This is the standard calculation. So you can you can compute one loop for brane loop. Yeah. Is this typical in Stony Brook? So my concern is that however you calculate the decay probability, if it is finite per unit volume, then there is an infrared divergence here.
Right, but we're talking about a situation where you cut it off.
Cut it off, but the cutoff. So
You can think of that as a cutoff at the field theory scale of order 1 over the ADS radius. So it's a pretty low scale from that point of view. I just want to make sure you're not proposing a no-go theorem on that because it's been a.
This is just the Horowitz-Poltinsky argument.
No, I know, but that applies because you have the boundary, and I'm saying once you.
He does have a.
No, he just he made a comment generalizing it to the cutoff case, and that's why I'm asking about it.
I mean, Horowitz-Poltinsky explicitly includes the incorporated.
Yeah, I'm talking about the warp compactifications or Randall Center where you cut it off, you couple it to gravity, and stabilize the whole system. I'm asking if anybody.
Okay. So in that case, cutoff is actually small. I mean, it's a small cutoff scale. So namely the geometry. So you have this kind of Randall-Sundrum brane or something like that over here, and the actually distance from between here and here is a physical distance. That is that for example the 100 TB or something like that.
Yeah, I'm just asking if you agree.
Yeah. So I'm not excluding that. But it's consistent. What I said is consistent with what I said because what I said is that if you cut off, then the decay rate is at cutoff scale.
What does that mean? You think the decay rate is RADS or sorry is.
So scale set by the size, the volume of this cutoff region. So you cut it off. Now volume is finite. Decay probability is proportional to that volume. So if you in Randall-Sundrum case, for example, if there is a physical scale, physical cutoff, then if there is this kind of instability in Randall-Sundrum scenario, then the probability is given by is proportional to that volume.
But their stabilization mechanism is the Goldberger-Wise mechanism. Does that fall under your classification of possible instabilities? Or?
Not necessarily, because there can be other mode of instability. Namely, that the kind of instability I'm talking about is happening in the bulk, where you have a brane nucleated.
Actually, explaining the connection to the dual description might be easier. The motivation on why it's unstable is then explained how the usual description of parallel branes. Why isn't there such?
Yeah. So one. Yeah. So you can say that, but well, here talking about the repulsion of.
That's the original description, right? How do you get the near horizon jump? You put branes next to each other, and if that's not stable, you cannot get the dual geometry. Here, if the tension is weaker than the repulsion one, so you cannot even have the near horizon jump. So from M less than Q, which is generalization with tension less than char, means that the repulsion wins. That's simple. So from the original description, it's kind of obvious there should be no group.
That's a motivation. I agree. And then, but the bulk can be constructed in other ways, so it doesn't cover all the cases.
I don't know if the field theory intuition was you can very well have theories that aren't UV complete and from the field theory point of view, so you better cut it off before you hit whatever problem that entails. But if you cut it off before then.
Yeah. But it's not the case that if you cut it off, if you protect your space by cutting off, then isn't the decay, the lifetime of that space being cut off scale.
You don't think it's exponentially long?
So what is the additional mechanism you are saying that? So you said there is a literature on that, so I'm not familiar with that. So can you explain what is sort of additional suppression in addition to? Because I would have so my argument was very naive. ADS is a homogeneous space. If it happens here, it happens everywhere with the same probability. So that means that the probability should be proportional to the volume.
You have to create this bubble, you have to nucleate it with
Yeah.
some size where its tension and its volume match, so you're creating a zero mass object.
Right, yeah.
And so that usually means it's big enough that the rate for that is...
Yeah, but I would have thought that the...
So if the rate is exponentially small enough size, now if you have the whole boundary, you have to integrate over all the places that can go, that even huge bubble can be. But once we cut it off like this, it can't.
Yeah, so you can certainly set it up so that the size of the typical size of the bubble is comparable to the cutoff, in which case you can avoid this problem, for example.
I think that's what these things
Okay, good. So that's is possible, but that's not our concern here, because our concern is that we are considering the situation where cutoff is very large, very far away. Where I'm considering the situation where when the non-supersymmetric ADS CFT allowing the possibility that CFT can be cut off in a very high scale. But then in that case, bubble would certainly fit. And but I think I agree that there might be such a way of protecting this space by taking this space to be small enough so bubble won't fit. I agree. Yeah. So thank you for clarifying. So this would clarify why there are still certain scenarios where this can stay stable. But nevertheless, the original premise of my concern with Cameron is that if you make this strict inequality as your claim, then the ADS, non-supersymmetric ADS CFT, as we normally understand, would not exist. And you can also state this in the CFT, pure CFT language. So if you can sort of formalize what class of CFT are expected to have bulk holographic dual. So for example, there are certain attributes such as sparse light spectrum, etc. And so you can, if you can condition that with CFT, then you may even be able to make this as purely CFT statement that whether, for example, bootstrap program works out for non-supersymmetric CFT with these additional conditions. So this is a sort of interesting direction to explore. So I had some additional note where I was trying to advertise my recent work with my grad student, Lev Spodineko, demonstrating some of the instability mode. But I'm clearly over time and the people are hungry, so I should stop here. So thank you for your attention. I forgot to make that point. That was a punchline of the talk. So yes, that's right. Thank you.